Question 5a. Complete table 5.1 to predict the substance liberated at each electrode during electrolysis. First, you need to know what's happened during electrolysis. The very important concept that you need to know is those cations and anions, they will try to discharge. So how to discharge? The cation will gain electron to discharge, means to let the positive charge now become neutral. The anion need to release electron to undergo discharge, means it's going to remove the negative charge from itself. So this is a concept during electrolysis. Both species, the cation and anion, they need to undergo discharge. So what happened when cation discharge? So as you can see from this table, the copper ion, hydrogen ion, and this lead-2 ion, all of that gains electrons and form these elements. So we know that anything that gains electrons, it must be the reduction. So means in order for the cations to discharge, it must undergo reduction. So means it's going to be a cathode. Means these reactions will happen at the cathode, because cathode is the place for the reduction. So which means all these cations, its reaction will always happen at the cathode. And therefore, the anion which always release electrons now, because its release electron, it's undergo oxidation. So oxidation means it's happen at the anode, because anode is the place for the oxidations to happen. So once you understand and know where is a place, then you can give the products, or else sometimes you might confused. So let's start with the first compound. So we have this lead-2 bromide, molten because it's liquid. So inside this liquid, it just have two ions, lead ions and the bromide. So therefore, this product is very easy. So the lead ion, lead-2 ion, will gain electrons and form the metals. So therefore, the substance that form at the cathode must be lead. For this anode, so we know that it's just a bromide there, no choice. So bromide must release electrons and form bromine. So at the anode, you see bromine, or you just put Br2. So from here, as you can see, from here, -1 to 0. So this is oxidation, isn't it? So this one is happen at the anode. And this lead-2 here is +2 to 0. So we know that is reduction. It's happened at the cathode. For the second solution, concentrated sodium chloride solution. For the discharge of the anion, I recommend you all to follow this trend. So you just remember this trend. So means whenever there is an iodide solution, for example, whenever there is iodide solution, iodide and hydroxide. Because when it's iodide solution, means the iodides together with hydroxide. So the iodide will always be the one that discharge, means form iodine. When a bromide solution, so bromide with hydroxide, so bromide also will discharge and form bromine. That's the trend. If let's say now we have a chloride solution, if the chloride solution is a dilute chloride solution, so it must follow this trend. So the hydroxide will discharge first. The chloride won't. This trend is for the dilute sodium chloride solution. When the hydroxide discharge, then it will form oxygen gas. If let's say now the solution is like this solution, concentrated sodium chloride, so the chloride will discharge first compared to hydroxide. It depends on the concentration. So when it's concentrated sodium chloride, okay, chloride will discharge. So once it's discharged, it will form chlorine, release 2 electrons. So that's why for this concentrated sodium chloride solution, you get chlorine. Again, if this is not concentrated, it's just a dilute sodium chloride solution, what we will get is oxygen. That's the difference. So for this substance liberated at the cathode, so because we know that inside it has the sodium ion and the hydrogen's ion. So the sodium ions, it won't discharge because its E naught means the reduction potential is highly negative. So it's more negative than the lead. So it's somewhere here, below here. So it's more negative than this lead. So when this sodium ion has the very negative reduction potential, means it's the species that more likely to donate electron. So it won't discharge. Because in order to discharge, it must gain electron, isn't it? So because the hydrogen's ion, or this hydrogen's standard reduction potential, it's 0, which is more positive than the sodium ion. So therefore, the hydrogen ion will be the one that undergo discharge, means it's more likely to gain electron and form the hydrogen gas. So that's why for this sodium chloride solution, the sodium ion will not undergo discharge. Hydrogen ion is the one that discharge because the reduction potential or standard reduction potential is more positive, more likely to gain electron. So it will form hydrogen gas. So you see hydrogen gas, you will not see sodium. For the last one, we have a copper nitrate solution. So for this nitrate, you can use back this trend. When there is a nitrate solution, means nitrate together with hydroxide. So hydroxide will discharge. So when hydroxide discharge, therefore it will form oxygen. Follow this equation. So hydroxide will form oxygen, release electron. So it's oxidation. So what you will see for this copper 2 nitrate solution, during electrolysis, at the anode you see oxygen because hydroxide discharge from oxygen. And now for the substance that liberated at cathode, because in this copper 2 solution, now we have copper 2 and the hydrogen's ion. From this reduction potential, we know that the copper 2 standard reduction potential is more positive. So we know that copper ion is the species that more likely to gain electron. So means it will undergo discharge first compared to this hydrogen's ion. So when the copper now gains electron and discharge, so it will form copper. So what you will see at the cathode is the copper. That's how you deduce or how you predict the products at the anode and cathode. First, you must understand what is happening. What is electrolysis? Part B, This question is quite challenging and quite confusing for some of you not really understand how to calculate using Faraday constant, numbers of mole of electrons, and so on. Okay, I try to explain in more details so you can understand how to deal with this question. Okay, so let's go. An electrolytic cell is set up to determine the Avogadro constant, L. And the electrolyte is a dilute sulfuric acid, and using both electrodes, okay, which is copper. During the electrolysis, the current used is 0.6 ampere, and the time that used is 30 minutes. So we can get the charge that used, Q equal to IT. So this is a very important info, because from these two info, we can get the charge that used. Okay, another important info now is the anode decreased in the mass by 0.35 gram, which means the copper now is dissolves and form copper 2 ions. And the one that decreased, so is the copper, okay, which to form this ion. So later we're going to use this mass to calculate the moles of the copper ions that form. And now, for part 1, before you start the calculation or to find the Avogadro constant, you need to know the relations between the Faraday constant and the Avogadro constant. In order to give this one, of course, you need to understand and know the relations. L is the Avogadro constant, is equal to the charge on 1 mole of electron. The charge on 1 mole of electrons is actually Faraday constant. Faraday constant tells us this one. The charge that carried by 1 mole of electron, that's Faraday constant. So when the Faraday constant over the charge of 1 electrons is actually the Avogadro constant, means it's the 1 mole of particles or 1 mole of the electron, right? So therefore we have this F over E. E is actually the charge on 1 electron. So therefore now we have this, the F therefore is equal to L times E. So means the Avogadro constant times the charge on 1 electrons. That's a relation. Part 2. I show you 2 methods to get the Avogadro constant. So please try to follow if possible. Okay, before you try to calculate something that you must get prepared. In this electrolysis, you must find out these few things. Find the moles of copper 2 that form, and after that, find the moles of electrons that involved. Means that released from these copper metals. And after that, find the charge that used to form this copper 2 ion. And after that, you must find the numbers of moles of electrons involved. Remember, the second and the last term, they are different. We will need to find the moles of electrons, and the numbers of electrons. They are different things. Moles of electron and the numbers of electrons you can relate using this one. Okay, so please recall back what you learned before this. In order to get the mole, we need to use this one. So the moles of something is equal to the numbers of particles over the Avogadro constant. This is how we get the moles of something. If let's say we use this one for the moles of electron, so in order to get the moles of electron, we need to use the numbers of electrons involved over Avogadro constant. That's the relation. So means if you want to find L, means the Avogadro constant, you must find these two terms. Most of electrons involved and the numbers of electrons involved. Then you can get L. I hope you understand what I say. Let's go. First, calculate the most of copper 2 that produced. So from the questions already told us is 0.35 over the molar mass of the copper, so you get the most of the copper ions form. When these copper ions form, we know that if you release electron, isn't it? 1 mole of copper ion form, it will form 2 moles of electrons. Therefore, when we get this moles of copper, we know that the moles of electron is going to be double. So this is the moles of electrons that produced during this electrolysis. So we get this one already, isn't it? Now we need to find another terms, which is the numbers of electron. So how to find? We need to use the Q equal to IT to find it. So we know that Q is the charge that involved, I is the ampere, T is the time in second. So 0.6 ampere times 30 minutes times 60. So now this one is a second. So you get 1080 coulomb. This is the charge that involves during this electrolysis. So how to get the numbers of electrons then? So the numbers of electrons, you need to use the charge or the total charge that used during electrolysis over the charge on 1 electron. So after that, you get these numbers. This is the numbers of electrons involved during this electrolysis when you use the total charge used over the charge on 1 electron. So is it now we get the another terms? So we can get the L now. We use the numbers of electrons involved, here, this one, over the moles of electron. Okay, from here. So therefore, we can get the Avogadro constant, which is 6.123 times 10 power of 23. So this is one method. I tell you another method. So this one is alternative or another method. From the question, again, it's already told us that 0.35 moles of copper 2 will form. So find the moles of copper using this. And in order to dissolve this copper, so we need to use this charge. So we'll calculate the charge first. So Q equal to IT again, you get 1080 coulomb. So this is the moles that form when we use this charge. So therefore, 1 mole of copper 2 needs how many? How many of that? So we need to use the ratio. 63.5 means the 1 mole over the mass that used, right, times 1080 coulomb. If you wonder how to get this, you just need to do the cross multiply. Okay, for example, 0.35 over 63.5 is a moles that used. Okay, we'll need to use this charge. So when 1 mole, how many charge that involved? So you get this relation. So basically we just use the larger ratio, means 65.5 over 0.35 times the charge that involved. So we will get the charge that involved for 1 mole of copper 2 ion. Is 1 mole of copper 2 ion. So we know that again. For this one, the electrons, the charge on the electrons, so as you can see, the charge that produce, this charge that produce the electron or the copper now is this one. So the charge that produce for the 2 moles of electrons also same, because same charge used to produce these two. That's why when we want to get the charge on 1 mole of electrons, so means we need to divide by 2. Means use this 195,943, this column, over 2. Because again, this is the charge that produce 2 moles of electron. So per mole of electrons, then we need to halve it. So this is what you need to understand. And after that, you get the charge on 1 mole of electron. So basically, you just use the 195,943 over 2 now. So we'll get this, the charge on 1 mole of electron. So recall back what I told you just now. L is equal to what? L is equal to the charge on 1 mole of electron over the charge on 1 electron. So, okay, this is a relation. So you use the one that calculated just now, the charge on 1 mole of electrons here, and the charge on 1 electron, this one will be given in the table. So you get this, the same value, 6.123 times 10 power of 23. So therefore, you get this Avogadro constant. Okay, I hope you understand. Thank you.